For air distribution systems, HVAC systems, we are not just interested in how much air is moving, but how air moves within and between spaces, right? The silica powders and chemical smoke are simple but powerful visualization tools, right? They are visualization tools that makes invisible airflow pattern visible. When released near supply diffusers, the diffuser that diffuse the air, supply air, smoke shows us air jet directions, velocity decays, and mixing behaviors. We can immediately identify where the supply air is actually going. Right? You want to supply air to go to the whole space. Okay, what we call the breathing zone. Again, those are terms that if we do the activity, we will learn about those terms. And whether, yeah, so whether the air supplier go to the space. These tools are especially effective for identifying airflow, what's called short circuiting. Just like the electricity, we don't like short circuiting, right? If a smoke travels, say, directly from a supply diffuser to a nearby return grill without spreading through the space, well, then the system is what? Guess what? It's conditioning the air, but not the occupant. We want the air to go through the space and therefore the occupant before the supply air being used, right? Being used, and then can be returned to the return duct. Okay, so if this happened, then that indicates poor diffuser placement, or maybe uh, different kind of problem, maybe velocity, inadequate mixing. We will need to solve that kind of problem, right? Smoke also help us locate source of air infiltration or leakage within the space. Unexpected smoke movement near the door, near the partitions, joint, ceilings, penetration may indicate pressure imbalance, right? So we don't want any of those unintended airflow path, right? Finally, by observing smoke movement between adjacent rooms, we can evaluate pressure relationship. For example, airflow consistently moving from one room to another indicates a pressure difference that may be intentional, such as isolation or washroom space, or sometimes unintentional, right? Unintentional. Then that will contribute to comfort and air quality issues. Right? So overall, smoke and powder tests are qualitative diagnostics. They don't quantify airflow rate, but they are extremely effective for understanding the air distribution quality, which is often where comfort and energy problem originated. Okay. When we evaluate HVAC system, air system, right, we are trying to answer one simple question: is the air being delivered at the right temperature, in the right amount, and in the right direction or location, to the right place? To do that, we rely on four measurement tools, right? Measurement tools. Temperature probe, yeah, we measure in temperature. We want the right temperature. And they are used to measure temperature, air inside the duct, air handling unit, by putting the probe upstream and downstream. You want to both upstream and downstream, so you know if the heating element, cooling element are working properly and as intended, right? And so we can assess heating, cooling performance, right? Performance. Identify temperature losses, check for uneven air distribution. Thermocouple are commonly used because they are compact, inexpensive. RTD, they, they, they are better in terms of accuracy if you need high precision measurement. The velocity measurement, okay, the velocity measurement tell us how fast air is moving through duct across supply grills. Tools such as van, hot wire, an anemometer, and in some cases pitot tubes, right, to measure pressure, allow us to evaluate whether airflow rates are good, appropriate. The measurements help diagnose if there's any blockage or leaking duct, and are essential when balancing supply return air for efficient operation. Right, for efficient operation. The infrared, we talk about infrared thermal imaging, right? They provide quick non-contact surface temperature measurement. Just you can, it's like shooting a gun, boop, and you know the temperature. They don't measure air temperature directly, but they are useful for to scan the surface, vent, equipment to identify hot, cold spots that may indicate maybe insulation problems or any malfunction component, right? For example, they can reveal thermal systems, thermal symptoms such as hot spot on motors, bearings, electrical connections, the ductwork, some cold, warm patches, right? If there's any missing insulations, air leakage, bypass, that's not good, right? Bypass. So uneven temperature across the coils, so on and so forth. Okay, very, very useful. Air, air pressure sensors are used to measure static and differential pressure within the system. Pressure measurement can identify if there's any too much pressure drop or confirm the fan operation, the pressure relationship between the rooms, right? Maintaining correct pressure balance, it's critical for energy efficiency and indoor air quality. Okay, so these tools allow auditors to diagnose performance issues, optimize system operation, ensure that the air system deliver comfort efficiently rather than wasting energies. Okay. Hydronic. So hydronic heating systems or cooling systems, it's a water-based system, right? Precise measurement of the flow temperature. It's also very important because water is the medium that transports energy, thermal energy. It carries thermal energy throughout the building. So you can see different types of meters here. The ultrasonic, this ultrasonic, Kalembang ultrasonic, they are the gold standard for auditors because they are not intrusive, right? You can measure the water flow rate through a pipe without shutting down the system or cutting into the plumbing. So we can use them to verify if the pump is actually delivering the flow rate, the design flow rate, which is critical. If a pump is oversized and, and moving too much, it will waste a significant amount of electricity. Okay, I don't know if you have you done the uh, what's the law? Affinity laws, right? The fan laws. Remember laws? But the flow rate, the the pressure difference, the new pressure difference is proportional to the new flow rate divided by the old flow rate bracket square. So anyway, we do not want to have a too high of a flow rate. It really wastes a lot of energy. And this one here, right, it's differential pressure flow meters. The reason we use them is the pressure drop across a known restrictions, right? We know this, we restrict this flow, make it a orifice plate, or and since the flow is proportional, right? The flow is proportional to, excuse me, again the same, proportional to the square root of the pressure drop. We can calculate exactly how much water is passing through a specific this branch of the system. Okay, and so by doing this, we have data to say balance the system, right? The auditor will use these meters to ensure that the every branch, especially the furthest branch radiator in the building, is getting enough pressure to function, preventing sometimes maybe hot in the front and cold at the furthest branch, right? We don't want that. Other methods we can use, again, infrared for quick non-contact temperature readings of pipes or heat exchangers. Right? In hydronic systems, the most important calculation is the temperature difference. The difference between supply water temperature, return water temperature, the what's that, Q dot equal to V dot rho Cp delta T, right? So that delta T, it's very important. And so using these flow meters, infrared thermometers, auditor can calculate the actual heating cooling load the system is currently handling. Right? Okay. And again, this, if there's any short circuit, we can detect as well. Right? We can detect them. If there's very low delta T, then something is not right. Right? Something's not right. If you use your infrared thermometer and find a return pipe, it's almost as high temperature, as hot as the supply. Something is not right. Okay, something is not right. All right. Now we electrical device. This is the most dangerous part of the audit, because I don't know. I don't know much about electrical. Right? But when I hear that, I'm always very cautious. Okay, know what I do before I do it. Anyway, we use standard tools like ammeters, voltmeters for professional audit. We also need what's called power quality analyzer. This device doesn't just tell us how much power is being used, it also tells us the shape of the power. Right? We are looking at the power factor and harmonics. Those are the technical terms that We don't need to worry too much about the theoretical meanings, but we do need to know what it is and how to deal with it in terms of from the energy audit perspective, right? Because we want to make recommendations. This is especially true for industrial and again, industrial large commercial customers. Okay. For electrical measurement in an energy audit, we first verify the building's power distribution. Always the distribution circuit, they are properly connected, or the wire properly rated, right? You cannot use too small of a wire for something. Let's not rate it at a certain at a larger where larger wire is required. Okay, and then measure and log real power, reactive power, apparent power, those right. This and therefore the power qualities. Okay, power system qualities, and also of course the total energy over time, right? The total energy over time, to understand both consumption and efficiency. Efficiency. Remember in the utility bill, right? In a utility bill, we will be billed if the if the power factor is too low, right? The customer will be penalized by paying a higher fee. Okay. Finally, we also check for harmonics, phase imbalance that can affect equipment life, and those are hidden issues that can overheat motors, damage stress transformers, and have a short equipment life. Now, at the equipment level, right, if we look at individual device, we measure the actual performance and efficiency to identify energy loss and operational issues. For lighting ballast, right, the ballast for the fluorescent lightings, right, we call ballast. It's the electronic controls. For LED, these days we call drives, right? The drives. It's also the control part of the lamp. But let's say a lighting ballast that we use for the compact fluorescent lighting. We measure the electrical input, light output, and also using a power meter to determine efficiency, detect any aging, poor match ballast, and that was electricity. Okay. Motors, we check for voltage, current, power factors, of course, and sometimes the speed as well, the speed, to calculate the motor efficiency. And we want a motor that is properly sized, because oversized or overloaded motor, oversized or overloaded motor, meaning undersized motor, can waste energy and shorten equipment life. All right. Combustion systems such as boiler, furnace, water heaters, we will want to know the fuel use, how much the fuel goes into those equipment. Stack temperature, because that's the temperature that goes, the flue gas, right? The hot flue gas that goes to exhaust. And if we can capture those energy, it's good. I mean, really good. If not, it will become a waste. And also what is in the flue gas, the exhaust compositions, right? And by looking at the composition, we can determine how efficient the combustion efficiency, or sometimes we can detect incomplete combustion. Okay, if it's incomplete combustion, meaning fuel not fully burned, energy not fully released and used, then we might see, say, more carbon monoxide rather than carbon dioxide, more oxygens, because oxygen is supposed to combine with the fuel and have that combustion process, right? Things like that. Back to ballast, right? The again, it's a electronic control that device that regulates current, voltage currents to the compact fluorescent or any kind of fluorescent lightings. There's mercury atoms in the tube, right? Anyway, and providing proper starting voltage and preventing, and then after, once that kickstart, right, you want to kickstart the lamp and then provide that current to regulate that current so it doesn't damage the lamp. Right? The older one, the magnetic ballast, they are old technology. If you, I don't know, are you old enough to remember or seen the ballast that you have that you can hear that that noise, and also the flicker sound, right? Those are the magnetic ballasts. These days we use electronic ballasts. They are more energy efficient, and yeah, okay, okay. Motors, this data logger again, and when we use this to evaluate motors at the equipment level, our goal is to understand how they actually operate in the buildings, not just what they are rated for, right? Three types of main measurement: the runtime, how long, like this on, this is the on is the runtime, right? You add the on time up, so you know how long they run. Excuse me. Runtime will tell us how long, how often the motor runs, and this can help identify underused or overworked motors. Okay, and help us to decide and support maintenance planning based on actual operating hours. Reveal energy waste from equipment running when it shouldn't. Okay, so yeah, so give us a lot of information. Second, we can take electrical measurements such as voltage, current, the real power. Voltage will tell us if the motor is being supplied correctly. Current indicates the load, and the real power allow us to estimate energy cost and efficiency. Right. So there's a lot we can look into. Like, it can even help us to find mechanical problems as well, misalignment, overloadings, right? And of course, the power factors. That's what we want to monitor as well. Show how efficiently the motor uses electricity. Low power factor means the motor is drawing more apparent, what's called apparent power than necessary. Okay, uh, and increase the losses and sometimes triggering the utility penalties that we saw earlier, right, in the previous modules. Okay. Yeah, so combining all this runtime data, electrical measurement, and power factors, we can you can see the motor loading, efficiency, temperature, the overall health, right? The overall health. Okay. Combustion system analysis. The fuel flow, how much fuel, we already mentioned all these points: fuel flow, stack temperature, exhaust compositions, and to calculate combustion efficiency, detect incomplete combustions. Those are the reasons why we want to do this measurements. Right? We want to find these opportunities. Okay. To reduce fuel use and maintain the heat delivery. Okay, heat delivery. The how efficiently and safely fuel is being burned in equipment like boiler, furnace, those equipment, and by analyzing the flue gas, if we look at what's in the flue gas, we can determine whether the air fuel ratio, you want to have the right ratio to have the best combustion as possible. Too much air is also not good. Like say, oh, why not just give tons of air? Well, we will actually lower the heat, the temperature if it's too much air, right? You just want the right amount of air. Otherwise, all the other extra air is going to suck the energy from the combustion as well. So the right ratio is important. How much energy is being wasted, whether harmful emissions are being produced, right? These are the questions we want to answer. The system measure key gases such as oxygen. You don't want to measure too much at the end. Carbon dioxide, you want to have mostly carbon dioxide because that's the product of combustion process. A little bit carbon monoxide, that's pretty normal. Nitrogen oxide, sometimes unburned hydrocarbon, the fuel itself, right? Oxygen will tell us about if too much air or not. Carbon dioxide indicate how complete the combustion is. And carbon monoxide is, well, we know it's dangerous, right? Carbon monoxide, it's critical safety indicator of incomplete combustion. Okay. Stack temperature, it's also measured, right? We want to know what is temperature of the flue gas, because if it's very high, can we do anything to reduce that temperature, meaning taking the energy out of it before the hot flue gas goes out of exhaust into the environment. Okay, so before, this is the last slide, right? Before we finish, just saying, don't forget about simple tools. Measuring tape, flashlight, paper, pen, pencils, this basic functioning tools. I mean, yeah, when you look at them, nothing special, but they are essential in every audit. I still use paper, pencils, pen for doing work, right? They are basic, but they help verify dimensions, inspect sometimes hard to reach areas. They help you to document conditions, record what instruments cannot capture. Okay, and good auditing isn't just about advanced technology, sensors, analyzers. It's about kind of a careful mindset, right? Careful observations, documentations. I don't, honestly, I don't like documentation, tedious, but it is important work. It is important work. Okay, and of course, attention to details. This kind of characteristic we want to, not just for energy audit, right? Not just for energy audit, for even our daily life. Okay. Yep. So that's I think this is module 5. Yeah, module 5. That's it. And hopefully you continue watching these videos, and yeah, we will discuss this in class again.